Hi, this is section 3 called the two-dimensional transformation on the plane. So recall that we have a line and the object we try to transform is just again another line. Then we have a plane, 2-dimension, but we only transform a line at a time by using vector operations. And now we are ready to use an object, a two-dimensional object, maybe a piece of paper or some shape, and transform it on the plane. What does it look like? Before we go into the details, I suggest you play this game called I think you have it on the screen. Yeah, called Transformation Golf. It is on this mouse. Don't worry about my headphone. 30 to 35 minutes. This is a teacher's perspective, but you can go to this blue button on the right and go to student preview, and then full screen, and you can play around as a student. So there are explanations, images, and challenges. When you go is to play a golf. In this game of golf, you can move an object, this purple object, an L shape to the hole or the destination. And there are 3 possible moves you can perform. You can translate, you can rotate, and you can reflect. And yeah, of course, you can translate one point to another. But the fun thing is, you can see what's going on here. It breaks, right? Because if you can do anything you want, it's not gonna be fun. So they add some kind of obstacle to make it more challenging. So yeah, you cannot reflect that directly, but you cannot translate that directly. But if you are clever enough, then you can see that actually we can, just like a golf, you can, what's the word, par it by hitting it 2 times. And here it is, we can chip it to the hole later. And interestingly, like if I ask 10 people, 20 students to do the same thing, there should be at least 3 different solutions. The first basic solution, which I just showed, is about just using translation. And so you are actually playing a golf and moving this object around. And there's something else that might feel more intuitive, like you see here we have a rotation. We rotate around a point, and there it is. We get kind of close to the result you want. But the nice thing is that you can also change the center of translation. In this case, if you do it cleverly and move the center to this point and rotate it again by 180 degrees, then voila, we got it. That's how you can accomplish that, by using a rotation. And lastly, or maybe this might be a spoiler, you can also use a reflection. This is tricky because it's a reflection. It doesn't work the way I want it to. It'd be like that. Let's do it this way then. Let's reflect that up. And then maybe reflect that this way. Let's rotate. But yeah, you get the idea. I mean, there are some sequence of moves or of putts you can perform until you get to the goal. And if you have time, I suggest you do all the exercises. Because the way this website, this mods work is that along the activities or games, and you can you can have this kind of screen where you can plot, you can draw, so you can sketch what you are trying to achieve. You can even type. like as if you are making a sketch on paper. And there's a multiple choice question where you can answer and explain things, and hopefully if we are in the same class, then other students can also join in and share your thoughts, their thoughts. So yeah, that's one. You can play with that. But let's suppose we play with that and get an idea. And this is what we are going to try to accomplish next. So we're gonna move the whole image from one point to another. This approach is more like geometrical approach, where you move things physically and get a result. But we can do that using math, of course. And that math, and again, of course, we're gonna use vectors again. That's a nice way to represent a point, and where we can perform some operations on that. So in analytical approach, we think of points as x, y. So at first, like when we talk about vectors, like we can see that okay, we can have a vector v and scale it up to k times v. Right, but all those operations are actually just just considering them as a point. So it's like we just move points around. We multiply a point, we add points, we rotate points. Right, but how can we accomplish the same thing, but in for a two-dimensional shape? Because you can see this shape has like what 1, 2, 3, 4, 5, 6 different corners. They also have lines and other stuff. Like how can we make sure that okay, if you perform some operation or perform some transformation on that object, and how do we make sure that everything we also move in the same way? So that's what we are gonna do next. The approach that we are gonna do next is if you know what you are doing, like for this exercise, for this interactive activity. Now we know that we are going to do translation, rotation, and reflection. There are 3 basic moves. If you don't want to, increase the size or screw it in various ways. Right, but what if you are given, an equation, or you want to perform a sequence of transformations and make them all, condense them into a single transformation? Is there a way to accomplish that? And the answer is yes, we can think of it as a function, but instead of a point, we recall that previously we have that as a point, and you get a new point. Right here, we can use a function as transformation on a vector, and the result is a new vector. It's hard to see, and maybe I shouldn't do that, but it's v vector and then the dash to indicate that it is something different. Maybe I should actually change it to v1 or something. But yeah, given a vector, you can transform it to a new vector. So that's what we use as a transformation of a point. Then what about a shape? How do we transform a shape? Like recall that in one dimension. It is a similar concept. Like in one dimension, we have an interval or a line segment. But we treat them. We cannot treat them as just 2 endpoints, and hope that whatever kind of transformation we perform, then the endpoints are still inside, still between these 2 points. You may move points around, you may flip, you may rotate, you may deflect, do all the fancy stuff, but we kind of wish on hope or cross our fingers that okay, everything else between these 2 points should still be between these 2 points. But let me make a note that is not always the case. It's always the case if this is linear. But if you if you use square or square root or all those fancy stuff, then this is not guaranteed. But again, for the linear transformation or the basic operations, then this holds. Now, what I mean by that is if you have these six points, 1, 2, 3, 4, 5, 6, that represent the shape of this object, of this L-shaped object. And then if you know where these points end, actually let's give them a name: 1, 2, 3, 4, 5, 6. If you know where they end, for instance, this is 1, this is 2. Let's say they end up in these two different directions. Then you can kind of like guess, or like connect the dots that if 1 and 2, if at first it has this orientation, 1 is to the left of point 2, but after the transformation, or after you apply that to some kind of equation, then the point 1 now becomes a point above the point 2. And that must mean we are doing some kind of rotation. And if it's a rotation, then all the other points should also follow the same rotation. No, kind of a rotation. And so again, we have this. Once we know how to map this point, then again, if we know it's linear, or if we know it's simple, then we assume that everything else also lie inside those lines. So that's the basic one. And then we can, once we know what it does with just one shape, then we can use the same, the same deduction or the same pattern on any other shape, like this square, this star, this circle. And then we know that, if this shape is rotated in this way, then every other shape should also be rotated, by the same pattern or by the same method. So let's say what I mean by that. Let's take a look at this example. And I think there's a website, but I forget what that website is. Oh yeah, and I don't even have it in the lecture notes. Oh yeah, but it is in the next section. Yeah, my bad. Maybe not next lecture, not now. Yeah, but what we have here in example 3. So in this, there are four sub-problems. In each problem, we have a vector. And this is a transformation. And this transformation is described as a new equation. So if you start at point xy, you move to a new point to x and y. For B, if you start at xy, you move to a new point x and minus 2y. If you are at C, if you start at xy, you move to y and minus x. And D, this is more sophisticated. If you are at xy, you move to x plus y and x minus y. And again, at a glance, there's no way you can, understand what is going on here. But the way you can guess, make educated guess, is that you consider a square that consists of these 4 points and see how those 4 points go, and then understand what is going on here. So let me give you an example for the first one, for A. And what do you mean by that is, actually we can do it on the right? Yeah, maybe it's better to do it on the right. So let's say that this is the original image. So let's think about them as these 4 points. Suppose we have these 4 points. And of course, we think of them as a square, a filled square. If you take a look at the file, if you happen to have an access to that, then you can see that I also color it to make it slightly easier to identify each point. Let me make this orange. Okay, so there are 4 points, 4 sections. Right, and let's take a look at the first one. The first one is trying to transform this point xy. For any point on the plane x and y, we multiply x by 2 and then keep the value of y. And what I mean is that, so let's take a look at each point separately. So if you have, if you think of the first point, 0, 0, or the first vector in this case. Then if you do the math, like x become 2 times x, so 0 becomes 2 times 0, and y is the same, so it's 0, 0. That means this transformation, whatever it is, like keeps the origin intact or keep it at the same place. Next we have let's say this point, this purple point. This is point 1, 0, or the vector 1, 0. And what happens to this purple point? You can see that, oh, you multiply the top by 2, so we get 2 times 1, then 0, which is 2 and 0. This point, like, gets mapped to this point. In a sense, it gets moved or shift. Actually, at this point, we can't see, we can't tell yet whether it is scale or shift. Right? Because sometimes you don't have enough information for that. But we will see in a moment that it is scale, not just just shift. Then what about the blue one? This blue point is 0, 1. The x is 0, y is 1. So if we have 0 and 1, then the result is 2 times 0 and 1, which is 0, 1. So again, this blue point is in the same place. It doesn't move. And then lastly, this purple, orange point, 1, 1, gets transformed to the point 2 times 1 and 1, which is 2, 1. So it is this point. It's a point 2, 1. So based on these 4 points, we can see that the result looks like a scale version. And these are all information we have. And then we have to use some kind of like deduction to fill in the blank and say that, oh, yeah, if they get transformed this way, then they must also be stretched in this way. So the result here is this image. You transform a unit square center at the origin. Oh, sorry, where the corner is at the origin, into a kind of a rectangle, I guess. Rectangle. So in a sense that if you have a cheat sheet, then you are scaling that this way. So yeah, based on the experiment and doing some math and using some observation, we can see that, oh, this is it's not a dilation. I think what we call is it's dilation, but it's in only one direction. Like it scale up. It is scale up, but only in x direction, not in the y direction. Which actually what we can see from the equation, like because the y value is fixed, but x is multiplied or is double. So it makes sense that the result is also a double version along the x-axis. So that's A. And we can repeat the same thing for B, C, and D. Let me skip B because you can see that it's similar to A. But because of the minus factor, actually let me write B real quick. Because of the minus factor, then the shape also gets flipped. So the purple and pink are the same, but the top of the square is flipped. We have these square instead. They got flipped and scale in the y direction. So that's B. And again, they are just dilation. C is more interesting. You move xy to y minus x. And here you can see that we sometimes mix up the coordinate. Which is again fine. That works. That's a linear transformation. But let's see what the result would be. So xy becomes y minus x. Something is going on here. So let's start from 0, 0. That's 0 minus 0. So again, the pink one stays the same. What about the purple one? 1, 0 becomes 0 minus 1. Okay, now that's more interesting. 0 and -1 is this point, or this vector down here. And I add point -1. What about the blue one? 0, 1. Where does it go? It goes to 1 and -0. So it's just 1 and 0, which is this point. And finally, can you guess what the last point goes to? Where the last point goes to? Like from these 3 points, 1, 1 goes to 1, -1. And you can kind of guess like, oh, if you have a square or a rectangle, and then the different angles still looks similar, then the last point should complete the square in a sense. And indeed, it goes to 1 and -1. So that's a point. And finally, you have to compare that with the original shape to compare to see the difference. So the original shape, and let me copy that real quick, because we need that for D as well. I can't. Control C, Control V. Okay. And again, the reason why we have to use colors here is because if you don't use colors, you will say, oh, it goes from this square to this square. So it may seem like we shift at first, but this is not what is happening right here. Because again, you can see that as a shift, you can see that as a reflection, or you can see that as a rotation. This is ambiguous. There are many ways you can transform the yellow square to the green square. And so that's why we have to identify the corners. Like how do the corners change? Like in this case, the corner, the bottom left corner, will stay in the origin. Like the blue corner, it was up here in the original version. It moves to the upper right corner in the transform one. Then this orange, right, is also moved, or in this case rotated to this point. And finally, the original purple, which is to the right here, it moves, or in this case, it gets rotated down to this point. And so, after mapping these points, we can see that, oh, this transformation, and what we are doing here is actually a rotation, because we don't flip anything. The order of the points are kind of the same if you read them clockwise. They're just, rotated or moved to a new point. But let's see. Now you can see that, based on just this simple transformation, there are actually more things to consider to make sure that we don't mistake rotation to shifting or translating. Oh yeah, not shift, but translate. Or reflecting. And lastly, we have D. D is interesting one, right? Because we start from x, y, and we have a mix of x and y. So a point x goes to x plus y, a point y goes to x minus y, right? Yeah, right. And you just do it one by one. I'm gonna do it fast because I want to save some time. But if you start at 0, 0, then again, it's still fixed to be at 0, 0. If you start at 1, 0, x is 1, y 0, then once you plug it in, then you get 1 plus 0, 1 minus 0, which is 1 and 1. If you start at 0, 1, you get 0 plus 1, 0 minus 1. So that becomes 1 and minus 1. And lastly, if you start at 1 and 1, you get 1 plus 1 and 1 minus 1, which is, okay, to be equal sign, 2 and 0. Now that looks not unfamiliar, that looks weird. But if you actually plot this out, you will see that it's actually something that you can understand and describe. Because this purple point stays the same. Like this blue point, like that was it was the upper left corner. Like goes to this part. This purple point. Like it was the lower right corner. It goes there. And the orange one goes here. And it's gonna take some time to digest, right? And compare these two again to the original and see what is going on here. Because interestingly, like this simple equation, maybe not simple, I don't know, but this simply looking equation, like gives you a result that actually has 3 transformations at once. It's like you combine them together and make something new. Again, based on just a simply looking equation or expression. Right? Because it looks like a rotation. Yes, there's a rotation involved. Right? But you can see that the points don't kind of match up. Right? Because if you just rotate that, then this blue point, which was on the upper left corner, should be here, right? If you just rotate that. If you rotate that by, let's say, 45 degrees clockwise, right, this way, from this point to this point, then they should be blue. But it's not. And that means, we do rotate, but we also reflect or switch points of the blue and the purple one. So there's a reflection involved also, which you can actually combine them together if you use, again, minus or something, but for now we have these two. And also, if you measure the length of this square, like at first we have a square of length 1. But now we have a square where the points are, maybe it's difficult to see here, but this point is 1, 1. This point is 0, 0. So to find the length of this side, then again we use the Pythagoras theorem and see that that one is square root of 1 square plus 1 square. This is 1, this is 1. So the hypotenuse on the diagonal has this length, which is square root of 2. So indeed, like we rotate, we reflect, and it turns out that we are also scaling or dilation. So you can see now that, now there's something interesting. And we combine 3 different operations or transformations using just plus and minus in a clever or interesting way. And we're gonna learn about that in a moment. Like once we are ready for the rotation. But for now, I just keep in mind that it could get more complicated once we allow this kind of expression. So that's the second example, or actually third one. And there are many pages because each of these pages is one of these 4 transformation. But and then we have these exercises. So that's the end of this section, and we're gonna wrap this up in the next section.